Now that we know how to draw Lewis structures, we're going to apply something called valence shell electron pair propulsion. This is under the molecular bonding. This is chapter 10. So we're going to look at how we can more accurately describe. So we started off talking about those structures. We're going to now make those structures more representative of the actual geometries that the molecules have based on physical properties. And then we will further try to represent the bonding using valence bond theory, which we will get into in a little bit. So first, we call this valence shell electron pair repulsion, or VSEPR. Some people like to call it VSEPR. And anyway, what VSEPR does is it is going to look at drawing your structures in such a way that minimizes the repulsion of electrons, or specifically electron pairs, either bonding or non-bonding. So this is bonding or non-bonding, so lone pairs, around a central atom. Okay, so we're gonna the first thing that we're gonna say about electron pair repulsion that we're going to use is that the amount of space that electrons will require in a molecule will depend on the type of electron pairs they are. So the pairs that need the most space or most room are lone pair electrons. They have the most repulsion, so they're going to need the most space. So they have the most repulsion between their electrons. Electrons in double bonds need slightly more space, and electrons in single bonds need the least space. So we can just note this, that need more space. So the single bonds tend to fit our model predictions very well, but we find that when we have lone pairs in our structures, that we see deviations from that. Okay, so we're going to go through. We're going to first look at some structures without lone pairs, and then we're going to see with lone pairs. Okay, for each of our structures, we're going to describe them using three main characteristics. We're going to do more at the end once we do hybrid orbital theory, but initially we're going to say what is the electron pair geometry, or sometimes it's just, we call it electron geometry. And that's looking at all the electron groups. That's going to be electron pair. Again, this will be looking at bonding and non-bonding. Bonding and non-bonding groups. So we're going to specifically be looking at, this is going to be the 3D arrangement of electron pairs around the central atom. Now, the electron pair geometry, there's less of these because it doesn't matter if they're lone pairs or if they're bonding or non-bonding. If you have two groups, you're linear. If you have three groups, you're trigonal planar, and so on and so forth. We find more variations in the molecular geometry. Which is going to look at how the atoms are arranged around the central atom. And so often those are always going to be the same with bonding electrons, but if you have atoms and non-bonding electrons, then geometry changes because now we're not including those non-bonding electrons in that geometric shape, and we'll have examples of that to show you what I mean. So this is the 3D arrangement of atoms. So again, when you have bonding electrons, those electron bonding pairs and atoms are the same, and so the molecular geometry and the electron pair geometry are equal, are the same. But when we have lone pairs on the central atom, they change. So atoms around the central atom. Okay, and so to summarize that, we can say, we'll do it in purple. So if no lone pairs on the central atom, then the electron pair geometry, or we can just simply say the electron geometry, is the same as the molecular geometry. Okay, so that's the first thing to know. We're going to go through all of the different structures where we have no lone pairs on the central atom first, and then we'll look at when we add those non-bonding pairs. So we're going to start off with, so this is just going to be simply the number of atoms attached to the central atom. And we'll start off with 2. So the example that we will use is CO2. There are lone pairs in the structure, just not on the central atom. And so our geometry are electron or molecular because it's the same. Oh, no Siri. Thank you. So in this case, we look at our bond angles. We'll do that first. So bond angle is 1, 2, 3, the 3 atoms in the line, and so this is 180 degrees. It's linear, and so this is linear. Okay, we can get so there's only, for each of these geometries, there's only one type of linear, and so we will find that there's a couple structures that have some linear molecules if you have enough lone pairs on the central atom, but that's in a bit. So if we add a molecule, or sorry, add an atom to the molecule, then we get 3. So we'll do this. There's lots of examples. We're just going to do this right here. Okay. And so we're going to call this. So if you look here, between here or here, here or here, this is going to be splitting at about 120 degrees. So this is trigonal, planar. Now, you can just memorize all these names. There is a way to help you remember them, and that just goes with the trigonal. This is always 2 dimensions, and this is always a 3-dimensional shape. It tends to be the pattern, not always, but often. The 2-dimensional shape is if you attach all the atoms that are not the central atom, and that makes a 2D shape. It's a triangle, and you put AL or trigonal. And then the planar is what happens when you incorporate, what shape do you get when you incorporate the central atom? Well, you just made it a plane. Again, go check this out on our that PhET sim. Super helpful to kind of visualize that. If you have 4 atoms attached, that's going to be, let's do methane. And so what we're going to do for methane is I have 4 things attached. And so I'm going to try to put 3 in the plane, the hydrogen, the carbon, and the hydrogen. And then 1 is coming out at me. So it's coming out. The other is going away. So I'm going to do dashed lines, kind of getting smaller. Okay. So what we would say here is that that this hydrogen is coming out of the screen. So it's coming out at you, and that this is going into the screen. getting a little smaller. That's one way of drawing the perspective. You can do it in other ways too, but trying to draw most of the atoms in the plane of the paper or screen can help you so you don't have as many of these wedges and dashed lines. Okay, and then our shape will be tetrahedral here, so that's a little different than what I just showed with the 2D, the 2 name, but tetrahedral. Okay, if we do 5 things attached, so let's do PCl5, 1, 2, 3. 3 things are attached. Oh. So it's a Cl, 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 and then we have 5, so we have 1 coming out here, and then 1 going away here. The bond angles, let's go actually back and do the bond angles of the tetrahedral. The easiest one to see is when it's all in the plane of the board, and this is 109.5 degrees. And again, that's not 90, and you can see it's not when you draw it in that way because we are not dividing 360 by 4, but we have a 3-dimensional space to do that. Here, we actually have 2 different sets of angles. We have the these angles between the chlorine that's on top, axial, and then the chlorine that's on the side or equatorial. And then we also have, if you rotate this such that if we rotate this whole structure just forward toward you, what you would see is you'd have, not there, you would have and then 1 chlorine would be coming out, 1 chlorine would be going away. But you would have this, so basically if we take this this phosphorus, this chlorine right here, and we rotate it forward so it's like in line with the chlorine, or with the phosphorus. And again, this is where that 3-dimensional modeling program really helps. You would see that this angle here is 120. So the angles between the CLs in the same plane are 120, and then between the CLs on top and in this plane are 90. So we have 2 sets of bond angles, 90 degrees, and 120. And so the name of this is trigonal. And because we make 2 pyramids, we have 1 pyramid there and then 1 down below, which is a little harder to see. This is bipyramidal. Okay, and then the last one we can do for no lone pairs in the central atom is 6, and so we have SF6. We can do that. So that's 1, 2, and then we have 2 coming out of the board, and then or out of the screen, and 2 going away. Okay. Now in this case, we have all of our bond angles are going to be 90 degrees. So everything is 90 degrees because we have 4 in this plane and up above. So this is also 90 degrees. So everything's 90 degrees here, and this is called octahedral. Okay, so those are your basic shapes, electron geometries. Now these, for example, octahedral, we can replace these fluorines with 1 lone pair, with 2 lone pairs, 3 lone pairs, and get different molecular geometries, even though they all have the same octahedral. So we're going to go back through and say, okay, for linear, what happens? We're going to remove an electron, and then for trigonal planar, for each one of these electron groups, we're going to add lone pairs. Now the book uses this like AX E type of notation where you can have a central atom and then how many atoms and how many lone pairs. I don't use that, but it's very formulaic and some people like it, so definitely feel free to use that if that's helpful to you. But we won't be using that, so we'll check that out in the next lecture.